Okay. So, I mean till last video classes we have seen that we have done up to DC circuit, DC first order circuit. Now we will start for your AC circuit. First what we will do, we will take the single phase AC circuit, then we will go for your resonance and as well as that maximum power transfer theorem for AC circuit, and then we will take that your 3 phase AC circuits, and after that we will consider single phase transformer. And and in the brief introduction everything has been discussed. It is only for the first year level, whatever little bit is there. Then 3 phase induction machine, there also up to equivalent circuit and few examples, and after that DC machine, that is DC motor mainly, right. So, first we will now we'll start with single phase AC circuit, right. So, before starting with a single phase AC circuit, what we have to see is that we have to what to call see that how EMF is generated, little some basic ideas, So, before giving mathematics and other thing, just for example, suppose you have two magnetic pole, this is your N pole and this is your S pole, right, N pole, and one coil is there, this is the one side of the coil, this is other side of the coil, this is side A and this is side B, and by some means it is called prime mover. Say this coil is revolving, it is rotating in the anti-clockwise direction, it is shown here, it is rotating in the this is rotating in the anti-clockwise direction, right. Now, when it is at in the diagram whatever it has been drawn, so it is actually in the horizontal position, right. So, flux actually this is N pole and S pole. So, when flux actually going to the downwards from N to S pole, right, it is going to the downwards, then this coil, this is one side of the coil, this is other side of the coil, assuming it is a single turn, right, and with that one resistor is connected here, such that whatever voltage is generated, so some resistance is connected such that your current will flow, right. But our interest is not like that at this level, only thing is that how EMF is generated, right. So, when it is a horizontal position, then this is this side of the coil and this side of the coil, this is actually will be outside of the your what you call that flux region, right, because this is basically your in between N and S, it is a constant magnetic field, but when this coil is revolving, it is cutting the flux, right. So, in this case, so this side and that side, this is our reference position. So, there will be no flux linkage when it is at the horizontal position. That means, if you look into this diagram from here to here, this side is A and this side is B, right. So, this is taking at when it is revolving in this way, this is shown, suppose it is moved or what you call in angle of theta, right, and theta is equal to omega t. So, but when this side is A, means just as this is a conductor, it is shows like this side is A and this side is B. So, this side, suppose when it is horizontal position, this side is A, and when it is this side it is B, say, right, and this position, when it is at this position, this flux are coming, this is from N side and this is from S side, forget about this drawing, this will give it up, right. So, flux actually this is coming like this. So, when it is a horizontal position, this side and this side, there will be no it will not link the flux. So, that means at this position that EMF induced at this position will be 0. That is whatever in the diagram it is shown. Now, it is revolving in the anti-clockwise direction, this way it is revolving, and suppose making an angle in theta. So, its angular speed is omega, say, then theta is equal to omega t. This is from your physics, you know, right. So, that means so this is at the position, that means this suppose, now let me clear it. Suppose this is your what you call, this side is A and this side is B. So, this breadth of this coil, that means this distance is equal to B, that means this A to B, right. So, this is your what you call, this is the breadth of the coil. So, this is B, right, and length of the coil, this is the length of the coil, this is your L, right. So, area of this one, right, if it is a rectangular one, it is L into B, this is the area of the coil, right. If it is in centimeter square, if it is in meter, you put in meter square, right. So, this is the area, A is equal to L into B, right. So, now let me clear it. So, this is at some angle theta, and this is your center, this is the center, right, and it is revolving. So, it is revolving this breadth actually, that means it is making a circle with diameter b, because this is the breadth, this is the breadth, this is the breadth, right. When it is revolving, it is making a diameter your b, and this is a circle is drawn, right. So, at any point a, some tangential velocity will be there. So, anyway, this point is a and this is L, right, and this is the vertical your what you call vertical component, say a n. There should not be any mix up with that. This is north pole and this is simply a n, right. It is not north pole or anything, it is simply your that capital L letter a n, and this is your m, and this is your o, the origin, this is your o, the origin or center, right, and this angle is theta, that is this angle is theta, then this angle is also theta, this is 90 degree. So, this angle is also theta, right, and this point is this point A, right. This is the your what you call basic understand, means when the coil when this position it will rotate say 90 degree, that means this position A will come here and this is your B and this point will come here. At that time, this if you imagine, you will find it is a single turn, you will find all the flux will link to this, that means voltage generated will be maximum, right. So, again it is moving, again will come, when A will come to this and B will come to this, it is revolving this way, this is A and this is B, and again it is horizontal position, at that time voltage generation will be 0. So, it is a cyclic process, right. So, so I hope you have understood, because directly if I give you directly that your sinusoidal current and wave, then feelings will be slightly different. So, I started with this kind of thing first, right. So, let me clear it. So, next is, so if you look at the voltage generated, so EMF generated on one side of the loop is BL V sin theta, that actually from your physics, high secondary physics. So, when the coil is revolving in a constant magnetic field, is EMF generated one side of the loop, it is because it is a loop, it is a coil A B, it is a coil, so it is a loop, it will be BL V sin theta, right. So, B actually flux density, that is in Tesla or Weber per meter square, and L I told you this is the length of the your L is the your this is the length of the coil, right, this is the length of the coil, right, and V is the tangential velocity, that V is equal to omega t, we will see later, and this is sin theta, this is BLV sin theta volts, right, and this side is the one side of the coil, this is another side of the coil. So, two sides, therefore, total EMF generated will be 2 BLV sin theta volts, right. So, just hold on. So, in this case, now V is the tangential velocity of the conductor, right. So, it will be B by 2, that is, it is B by 2 means the radius, right. So, this is the diameter, B is the breadth, basically when it is revolving it is actually diameter, right. So, B is equal to your what you call the diameter. So, it is basically B by 2 is the radius. So, omega V is equal to your V is equal to basically your 2 pi nr, right. So, nr and r is equal to your B by 2, this is your B by 2. So, that is why 2 pi nr, right. So, that is B by 2. So, that is equal to pi bn meters per second, this is your tangential velocity, right. N is given speed in rps, revolution per second, B is the breadth of the loop in meter, I told you, L is the length of the one side of the loop in meter, and B is equal to flux density Tesla or Weber per meter square, right, and A is equal to, I told you, the LB, the area of the loop in your what you call in square meter or so in this mathematical expression, that A will be in the meter square, right. So, this is from your high secondary physics. Now, suppose, let me clear it. Now, therefore, EMF generated in the loop will be E is equal to small e is equal to your this small e is equal to 2 pi BAN sin theta, right. So, what you do in this expression, let me clear it. What you do in this expression, right, you know that BLV sin theta, you put in this expression V is equal to pi BN, I mean if you put in this expression, it is 2 BL into your pi bn, right. So that is equal to V, then your sin theta. So L into B, this L and B is equal to A, and you put in this expression, then it will become, put in this expression, then it will become 2 pi BAN sin theta volt, right. So let me clear it. So in this case, this is your 2 pi BAN sin theta volt. Now if the loop is replaced suppose by a coil, so you have n number of turns, right, you have n number of turns, then total your EMF generated will be, that in the coil will be 2 pi BA, you multiply this term, by capital N, N is the total number of turns, say. So it will be 2 pi BA capital N into small n sin theta volts, right. So is equal to, we can write that that means the maximum value of the EMF generated, EM, will be 2 pi BA small n into capital N, right. This is the maximum EMF generated, right, and if you want you can put this much of volts, right. So an instantaneous value of EMF generated in the coil will be, then E is equal to EM sin theta, right, is equal to 2 pi BA capital N small n into sin theta volts, right. This is the thing. Now theta is the angular displacement in time t second. So let me clear it. So in this case, when this coil is moving, right, I mean this is rotating, rather it is rotating. So theta is rotating. So theta actually is equal to omega t, that is 2 pi n t, because it is rotating. So let me clear it. So that means if you put like this, your theta is equal to omega t, that is 2 pi n t, omega is angular velocity in radian per second, then your what you call, then this equation, that this equation E can be written as your EM, right, then your sin omega t, right, because theta is equal to omega t, we are replacing theta by omega t, and this is your EM. So E is equal to EM sin omega t. So this is the expression for the sinusoidal voltage, right. So E is equal to EM sin omega t. EM is the maximum value of the voltage generated, right. So then this is the sinusoidal EMF, that E is equal to your little bit we have to understand here, right from the beginning. That's why we have started from the scratch rather than going to the phasor and other. First we have to this, because complex number will be involved again and again here, right. So E is equal to, now I told you that E is equal to your capital EM sin omega t, right. So this is actually this your what you call, so if you plot it, so this is from 0 to 2 pi, it is completing one cycle, right, because this is going like this and going like this, and continuation, it is continuation, and theta is equal to omega t, right. So this is your maximum value, this is your maximum value EM, and this side plot is actually E is equal to this thing, the maximum value, and this side is your what you call, this is, it is cycling, so this side is a minus EM, this side is a plus EM, and this is 0, this is pi by 2, this is pi, this is your 2 pi, right. So this is theta is equal to omega t. This is for your what you call, for your single, if you look into that, it has n pole and s pole and single pair of poles, right, sorry, see your one pair of poles. Now if an AC generator, so let me clear it. Now if an AC generator has p pairs of poles, right, when you have n pole and s pole, right, so it is one pair of pole, so it is p is equal to 1, because we are taking up a pair, not two pole, 4 pole, we are taking pair of poles. Suppose if you have, let me delete, if you have, look at this your what you call, just hold on. Suppose you have here, I have made it initially here. Suppose if you have here, it is n pole, here it is s pole, n pole, s pole, and it is revolving like this. It is revolving like this. So here in this case, you have p is equal to 2. That is 2 pairs of poles, right? So here it is ns. So 2 pair, your p is equal to 2 pairs of pole. So if it may be more also, it doesn't matter. So when we are talking here, we will talk pair of poles instead of number of pole. If you say number of pole, then in this case it is p is equal to 2 poles. But when we are talking about pair of poles, it is 1 and 1 together. So it is one pair of poles, that is n and s. And here it is P is equal to 2 because 2 pairs of poles, right. So, if it is so, then therefore, if an AC generator has P pair of poles, its speed and n RPS, the frequency is equal to, the frequency can be f, this small f can be given as number of cycles per second, right. You have heard that our frequency is 50 hertz. In Indian system, our thing is actually 50 hertz is commonly practiced in India, most of the countries. In USA, Canada, it is 60 hertz, and in Japan, I think it has 60 hertz and 50 hertz, both are there, right. But India is 50 hertz. 50 hertz means it is 50 cycles per second. This is the frequency, right. So, 50 cycles per second. So, that means so in this case the P is the number of cycles per second. 50 hertz frequency means it is 50 cycles per second, right. Here you show it is 1 cycle. So, if you have sinusoidal waveform, so it will complete 50 such cycles in 1 second, right. Then you can find out 1 cycle will be completed by 1 upon 50 second, that is 0.0 or what you call 0.02 second, right. So, now question is that this number of cycles per second, that is f. So, this can be written as number of cycles per revolution into number of revolution per second. I mean, if you write like this, it is number of cycles per revolution. So, you can write number of cycles per revolution into number of revolution per second. So, it is revolution per second, right. So, number of revolution per second. So, in that case what will happen? So, it basically it will cancel and it will become number of cycles per second. So, that is why number of cycles per second we are writing number of cycles per revolution into, this is into number of revolution per second, right. So, number of cycles per second actually it will be number of pair of poles, right. So, if you have 1 pair of poles, it will make your what you call, it is number of cycles per revolution, it will make 1 cycle per revolution, that is your, it is it is electrical thing. So, in this case that is why it is n pole and s pole, that here I have written ns, right. So, it is electrical thing, although if it will make your one rotation, if it is only n and s pole, then it is 1 cycles per second, right. But if it is made if you have 2 pairs of pole, although it will make your what you call that your 360 degree rotation, but electrically it is not, right. So, electrically it will be 2 cycles, right. So, that means here if you look into that, it is P is the number of cycles per revolution, right. So, if you have 1 pair of pole, that it will make 1 cycle per revolution, because it is electrical quantity, it is you are not looking at the mechanical thing, we are looking at the electrical thing, ns. Suppose that means in that your what you call, in that your what you call that this diagram, here you have 2 pairs of poles, although it will rotate your mechanically 360 degree, but it will basically complete 2 cycles, because it will swipe ns and ns, this way flux will link. So, that is why this your what you call, that is why number of cycles per second is number of cycles per revolution into number of revolution per second. So, this will be P into n, that means P is equal to, this P is number of pole pair. If you have 4 pole pair, if you have 4 poles, that means you have 2 pole pairs, this is pole pairs, right. So, 2 pole pairs. So, in this case your number of cycles per revolution means it will make 2 cycles per revolution, although mechanically it will rotate 360 degree, but electrically it will make 2 cycles per second, right, because you have 4 pole, that means 2 pole pair. So, later when we will learn your much more thing in the, if you are an electrical engineering student, when you will go for your second year or when you will study electrical machines, at that time you will learn much in detail, right. But this course, just to give you some basic ideas, this is the idea, that if you have number of pole pairs is equal to number of cycles per revolution, this you have to keep it in your mind, right. So, for example, that one small example I have taken for a 4 pole generator, right. So, and frequency is 50 hertz, say f is equal to 50 hertz, right. Then n is equal to f by p, because f is equal, this is the formula, f is equal to np, this is the formula, this is the f is equal to pn, right. So, n is equal to then f by p, and if f is equal to 50 hertz and p is your what you call, it is a 4 pole generator, that means P is equal to 2, because it is 4 pole means 2 pairs, N and S it has to be there. So, basically 2 pairs. So, that means 50 by 2, it will be 25 RPS, right, revolution per second, and if you 1 minute is equal to 60 seconds, so multiply by the 60. So, it will be 1500 RPM, right, revolution per minute. So, that will be your N. I hope you have understood this, right, because before going to AC circuit or average value, mean value and other thing, I hope you have understood this, that how EMF is generated. Instead of directly starting by taking E is equal to Em sin omega t or I is equal to Im sin omega t, I thought that I will start little bit with this kind of concept, such that your our understanding will be little bit better, right. So, that is why I have started with this one first, then we will come to the mean value and average value. So, this is an idea to give you how EMF is generated and how the your load and other thing is connected, that is beyond the scope at the first year level. So, that is why just let me clear it. That is why your in this diagram this part, that this is a load, right, and this is connected, I did not mention anything, because at this stage not required, right. So, only when we will study DC machine or DC motor little bit, at that time I will tell you similar philosophy, I will tell you how it is converted to DC, because this AC quantity is generated, right. So, to start with AC single phase circuit, I thought this will be the best one, and this side is upper side is N and this side is S, right. This is the flux moving from N to S, by coming from N to S, right. So, this way this is the sinusoidal EMF generated. Instead of taking E is equal to Em sin omega t, I have taken this one just for your understanding only, right. Now, we will come to mean value, that is average or average value or mean value we call, and RMS value, or we call effective value of an alternating current, because it is alternating, because it is moving plus minus, so alternating current, right. So, and it is symmetrical, sin omega t is symmetrical, right, symmetrical waveform, right. If plus and minus side both are same, area if you look the plus side and minus side, it is same with the same your what you call time interval, right. So, this is average mean, and this is RMS, sometimes average value we call mean value, and RMS value, that is root mean square value, we will see what is this, is called effective values of an alternating current. Now, here for our understanding, what we have done is, here we have not taken your what you call a sinusoidal waveform like that. We have taken some waveform, but symmetrical. If you look into this side and this side, it is symmetrical, this side is symmetrical, and this is this time period is t, say 0 to t, and this is your this time is t by 2, right. This is t by 2, and this is there is 1 2 3 4 5 6 if you take in second and second, right. Now, suppose at every this it is a sampling instant also, now you tell, right. So, at this point it is I1 and this is I2, this is I3, I4, I5 and so on. Every your sampling instant or every time whatever you take, the way you take, right. Suppose this I1, I2, I3, up to this you will come up to t by 2, right, up to t by 2 will come. Now, this is the current, this is the say current waveform, we will come to this later. So, this is the current waveform. So, the average value over a half cycle, that is I average, I capital you have taken, I average is equal to I1 plus I2 plus I3 up to IN. I mean you take all the value I1, I2, I3 up to INV and IN divided by your N. You have to consider up to this time interval up to N. So, this is actually the average value, or you can do like this, or average value will be find out the area under the curve. This is the and we will make it only over the half cycle, is because this is positive side, this is negative side. So, it is symmetrical. If you take average value for the full complete cycle from here to here, it will be 0, because this is positive area, this is negative area, it will become 0. We will not do that. For symmetrical waveform, we will just go up to your half cycle. So, only up to this. So, up to t by 2, not as a whole, because from this one it will be 0, right. So, that is not interest, or in a half cycle. So, average value over a half cycle, that is why it is written over a half cycle, it is I1 plus I2 plus I3 up to this one by N, this is the average value, or this one you make area over half cycle. So, this is the area over the half cycle divided by the length of the base of half cycle, and this length of the base of half cycle is t by 2 up to this, right. So, let me clear it. So, that means this is my t by 2 and this is t, and this is the base t by 2. So, that means that is divided by the length of the base of the half cycle. So, area of that suppose this I expression is known to you. So, you can integrate 0 to t by 2, then I into dt, because this is the expression for I. This is a some, instead of taking sinusoidal, some symmetrical waveform I have taken, and this divided by your length of the base of the half cycle. So, this is t by 2. So, 1 upon t by 2. So, this is your average value, right. Later we will see the expression, this is the average value. Now, next is that we have to come to the root mean square value, RMS value or effective value, right. Let me clear it. So, in this case what has been done, that suppose this plot is I square plot, this is I, and if you plot I square. So, it is coming like this, it is your t by 2 and this is t and this is the origin, this is I and this is I square, this is I square plot, right. If you plot the I square from it is this your what you call that, if when you try to find out the root mean square value, this area, this is positive side now because it is square, this was negative, but if you square it, it is going like this. So, if for making your RMS value half cycle or full cycle, it will give the same result because area of this one and area of this one is same. So, anyway we will consider this half cycle only because these are same area. If you consider 0, if you consider 0 to t by 2, right, if divide by t by 2 or 0 to t divided by t, in that case both will be covered. So, ultimate meaning is same. So, we will consider only your what you call only the half cycle, right. Even if you take the full cycle for RMS value, it will give the same result. So, let me clear it. So, in this case what is happening, similarly like here I1 at suppose 1, 2, 3, 4, you can calculate your, this is I1 square, this is I2 square, this is your I3 square, like this. Here it is I1, I2, I3, but this is square because this is square, right. So, whatever value we will get, this is I1 square, this is I2, this is 1, this is 2, this is 3, like this up to t by 2 and this is t, right. So, if you have some n such value, before going to that in terms of t, if you have some n such values, right, then it will be your average, your what you call root depends on the heating effect, that is the square of the current, because in DC circuit you have studied that power loss is equal to I square R, right. So, root mean square value depends on the heating effect, that is square of the current. As soon as we are taking in terms of square of the current, basically it depends on the heating effect, because I square R we have seen, I square R loss in the DC circuit, same will be applicable to your AC circuit also, we will come to that. So, therefore, the average heating effect is proportional to I1 square plus I2 square up to In square divided by n, right. You have such n such I1, I2, In square values and divide by n, right. This is the average heating which is proportional to, this is proportional to, right, I1 square plus I2 square up to In square divided by n, right. So, let me clear it. So, in this case, suppose now how we get the RMS value, suppose I be the value of the direct current to produce the same heating in the same resistor as produced by by alternating current, right. So, we have to assume something that I be the value of the direct current to produce the same heating in the same resistor as produced by the alternating current, right. So, then what we can do is we can write I square is equal to I1 square plus I2 square up to In square divided by n, right, or I is equal to square root of I1 square plus I2 square up to In square, sum it up divided by your n, right. This is total square root, or this one basically this is area of this curve, I square curve, this curve only, and this is your time t by 2, this is t, we will take half cycle. So, this is your t by 2, therefore, this is area of I square curve divided by the length of base under root, this is under root area of the I square curve. So, this is the area of the I square curve divided by the length of the base, that is your t by 2, 0 to t by 2. So, it is t by 2 minus 0, so t by 2 your base. So, length of the base, that is over a half cycle. Even with full cycle also it will give the same result, because this area and this is symmetrical. So, it has the same area, right. So, over a half cycle. So, that means this can be written as your 0 to t by 2 I square dt, and this is your little bit, this is your t by 2, 1 upon t by 2, right, 0 to t by 2 I square dt, right. So, this way you can find out that what is the value of your what you call I value, and this is called your RMS value, root mean square value or effective value, and average value sometimes we call mean value, right. So, that means, let me clear it, that means for average value directly we are taking half cycle. For root mean square value, first we are squaring it, square that your I square, right, and accordingly that heating effect actually proportional to the your square of the current. So, it is average heating effect is proportional to this, right, this, and therefore, I square we write like this, I1 square plus I2 square plus In square upon n, and therefore, I is equal to square root of I1 square plus I2 square up to In square by n, right, this is n, right, and is equal to square root of area of I square curve by length of base over a half cycle, everything I have written. So, this is basically square root of 1 upon t by 2, then 0 to t by 2 I square dt, right. So, now if you come to this, the average and RMS value of sinusoidal voltage or a current. Thank you very much. We will be back again.